trigger circuit. We have three parts in this subsystem, namely the IR sensor circuit, which works on the principle of obstacle detection. Then we have the piezo sensor circuit, which works on the principle of pressure application, as well as and we have the logical circuit, which takes on the digital input from the two TIIC sensors. That is this circuit. Now let's take them one by one. First, the battery is connected to the 7805 IC, which chops the voltage from 9 volts to constant DC 5 volts. Now this output is fed to the IR sensor as input, clearly. Now we have a pair of RX and TX here and are connected in the circuit diagram as shown in the figure. We have taken the analog output and fed the analog output to the operational amplifier in IC LM324. Here is the IC LM324, which is a quadruple amplifier, and into the non-inverting terminal. Now in the parallel run, we also have taken the piezo sensor circuit with the circuit diagram as shown in the figure. This circuit is used as a false alarm prevention circuit. The output of this circuit is also fed into the LM324 quadruple, one of the amplifiers of quadruple amplifier LM324. Now both the outputs of LM324 are digital high or low outputs, and they are fed to the sensor output in the logical AND gate. Now these outputs are then fed to the logical AND gate, and then finally the output is high or low when both of them are high. For example, we can see into the circuit, when I have put my finger over the IR sensor, it becomes it gives a high output from the operational amplifier, as well as when I have pressed the pressure on the piezo sensor, it has given high on the operational amplifier 1, but the final output LED is not lit. Now when I press the amplifier and I give my high command to the IR sensor, only then the output LED is high, and that means when both the circuits give digital high signal, then we have the final trigger to the Arduino board. Now let's quickly check whether our device is ready to take the inputs from our terminal. Yeah, since the C pin is given ready, that means our device is ready to take the inputs. Therefore, we define this CMGF value equal to as 1, and the return is OK. Every time when the command reaches the GSM module, it returns an OK command with signal that it receives. Now this command is basically a command used to send the message. Let's say I am using the cell phone number as given, because the cell phone number I have with me on the other screen is the same. Now when this arrow mark comes here, that means that we have to type the message. Let's say I'm typing the message hi, and this message will be sent on the cell phone. See, the message we have received from the cell phone is, therefore we have got the message from here, and our message has been successful. Our communication with the laptop and mobile is successfully established. After we have completed the introduction with the GSM and the FDS, we now introduce the GPS module. Here we have SIM28 module, which is a GPS receiver unit. In this we have connected the device with a microcontroller for the supply. Since it's a substantially low power device, therefore we can give directly +5 and ground voltage from the microcontroller. This subsystem is also connected to the computer by serial communication cable. Here is the antenna for the GPS receiver unit, which approximately works at 1500 MHz frequency. I'm setting up a new connection in the name of TI_GPS. All the driver details, since our device is connected on the COM port 6, all the driver details are pre-configured into this software. Now as soon as we set up the connection, we have many message strings repetitively given by the output of the GPS receiver. The NMEA dictates how each string is formed with the $sign leads to each new GPS message. We are receiving commas in the middle of the string because we have kept the GPS antenna and the receiver module within our not in the open sky but in our laboratory. Now, out of the 4 standard strings, GPGGA string contains navigational data, which primarily includes the UTC time, latitude, longitude, and number of satellites connected, along with the number of other relevant data. This is our entire system over here. We have got the GPS module here, we have got the triggering circuit, this is the GSM module, this is user cell phone, and we have the face detection system in the MATLAB. For the triggering circuit, we have the following components. We have got 3 analog ICs and 1 digital IC. In the 3 analog ICs, we have the first we have the IR sensor, second we have the piezo sensor, third is the logic circuit as explained in the previous videos. Now, when I give high output from both the sensors, I get a high command on the Arduino board. When the Arduino board receives high command, it sends a actuating signal to the FDS. But on the FDS, when I send this high command, we get the signal. We get to enter the image that we want to sample. That image will be taken by the camera. Suppose I am testing the image number 12 in this. So the image is being processed in the FDS. This is our image, and once when this image has been processed, since this image is not matched with the existing database, therefore a message will be sent to the user's cell phone. Here we have received the message from the user's cell phone, and it says that our car has been detected at so and so latitude and so longitude at this particular time. These latitude and longitude positions were sent by the GPS module over here, and this string was extracted by the controller board and was further sent to the GSM, and it was sent on the user's cell phone. Now let's restart the program again. Let's say this time I'm comparing the image number 11. When this image is being processed, we get the image output as this, and both the images, since it matches, therefore we get the message on the FDS system that all is working fine, and there will be no action taken by the FDS to actuate the GPS or the GSM. So this is our entire system that has been working fine and perfect. Thank you.